There are a few factors that affect the solubility of slightly soluble salts. The common ion effect, or adding in a common ion, changing the pH of the solution, and forming complex ions. We'll talk about each of these factors individually and how it will affect the solubility. We previously learned that we could calculate the KSP, which is known as the solubility product constant of a slightly soluble solid, if we knew the molar solubility. So for example, if we had a solid calcium fluoride, we know that that would dissociate into calcium 2+ ions, and we would get 2 moles of fluoride ions. If the molar solubility of calcium fluoride in water is 3.39 times 10 to the negative fourth, that would also be equal to the concentration of calcium ions in solution, and the concentration of fluoride ions would be equal to 2 times that value due to the stoichiometry. So the fluoride ions would be 6.78 times 10 to the negative fourth molar. Then we learned that we could substitute those concentrations into our equilibrium expression. Our equilibrium expression, our KSP, would be equal to the concentration of calcium ions times the concentration of fluoride ions squared. And that for calcium fluoride in pure water comes out to 7.4 times 10 to the negative 11th. We also learned that you could look this value up on a chart for a lot of common slightly soluble solids. Next, we're going to talk about how our concentrations or our molar solubilities will be changed if we introduce a common ion into our slightly soluble salt. So next, let's imagine that we have a solution of calcium fluoride again, but now it's dissolved in a solution of sodium fluoride. The sodium fluoride really would break up into sodium +1 ions and fluoride anions. So in this case, the part that's common to our calcium fluoride would just be the fluoride anion. The sodium would just essentially be a spectator ion since it's not a common ion to our overall equilibria of our slightly soluble salt. So in this case, we could think about how, according to Le Chatelier's principle, our solubility must shift due to adding in that common ion. So essentially, we're spiking our solution with extra fluoride ion by adding in that sodium fluoride. So the fluoride ion concentration would increase, and according to Le Chatelier, we're going to shift away from the addition. We're going to shift away from that excess fluoride ion, so we would shift to the left. And when we shift to the left, we're shifting towards our undissolved form, or the solid calcium fluoride. So essentially, our solubility will end up decreasing since we're shifting towards the solid form and we're shifting away from these aqueous dissolved ions. So adding in a common ion will end up decreasing the solubility of your slightly soluble solid. It'll get less soluble overall. And if we look at our equilibrium expression, our KSP, that's a constant value. At a certain temperature, that's always going to be a constant. So if our concentration of fluoride ion increases, then the concentration of the calcium ions must be lower. It must decrease since that KSP is a constant, and we still have our same equilibrium expression. It's still the concentration of calcium ions times the concentration of fluoride ions squared. But that KSP value does not change. That is a constant. If we look at the graph on the right, what we can see is that as the concentration of our common ion increases, our common ion is sodium fluoride, and as we go from left to right, the concentration is getting larger. The molar solubility of our solid calcium fluoride, or how many moles will dissolve per liter, is decreasing. It starts out in between 10 to the minus third and 10 to the minus fourth in pure water, where the concentration of sodium fluoride is 0, and as that concentration increases, it's dropping exponentially. So it falls all the way down to 10 to the negative ninth when we're at a 0.2 molar concentration of our common ion. So really the reason is that this happens is due to Le Chatelier's principle. So we still have the same overall expression for the dissociation of our slightly soluble solid, but anytime you spike it with a common ion, you're increasing something on that ion side, so you're going to end up shifting away from that and shifting back towards the left in favor of your solid substance, which is not dissolved. So you're decreasing that solubility. We know that our molar solubility should be less when we have a common ion present. We can calculate what that new molar solubility will be. Here we have the molar solubility of calcium fluoride in 0.1 molar sodium fluoride being calculated. So the first thing we want to do is still write the dissociation of our slightly soluble salt. So calcium fluoride will break up into 1 mole of aqueous calcium ions and 2 moles of aqueous fluoride anions. We can also write the KSP expression, or our equilibrium expression. So KSP will be equal to the concentration of calcium ions times the concentration of fluoride ions squared. And if we think about this essentially like we did when we learned our ice tables, we can think about how we would have an initial concentration, some change in that concentration, and then an equilibrium concentration. Also recall that we do not include pure liquids and pure solids in our equilibrium expression, so we're going to have nothing under the calcium fluoride solid substance. Our initial concentration of our calcium ion would be 0, and since this is a common ion, our initial concentration of that sodium fluoride is going to contribute 0.1 molar to our concentration of that fluoride ion initially, because our sodium fluoride substance has a concentration of 0.1 molar. And when it dissociates, it really breaks up into sodium ions and fluoride anions. The concentration of sodium ions in solution will be 0.1 molar, and the concentration of fluoride anions in solution will be 0.1 molar. So we have a concentration to plug into our fluoride ion spot right off the bat. We're also going to form some calcium ions and some more fluoride ions when our slightly soluble solid dissociates. So the calcium ions will be formed, and they will be plus X, and the extra fluoride anions that are formed would be formed in the ratio of plus 2X. The 2 comes from the fact that we have a 2 out in front from our stoichiometry. So our equilibrium line would be X, and it would be 0.1 plus 2X for our fluoride. Now, our KSPs are all going to be very small. The K values here are relatively small due to the fact that the salts are not going to be very soluble. So we can look up on our chart the KSP for the calcium fluoride, and our chart says 3.9 times 10 to the negative 11. Recall that when you have a very small value for your K, you can ignore X's that are added or subtracted. So that means that due to that being so small, we can ignore this plus 2X when we plug it into our equilibrium expression. So we're really just going to end up plugging that 0.1 into there. So our KSP, we have 3.9 times 10 to the negative 11. That will be equal to concentration of calcium ions, which our equilibrium line says is X, times the concentration of our fluoride anions. We're going to ignore the plus 2X, so it'll just be 0.1 we plug in here. And that'll still be squared, though. We don't want to forget to square that. So now when we solve for X, or our concentration of calcium ions, that is equal to our molar solubility as well. So they both will have a coefficient of 1 out in front. So it's essentially like saying the concentration of calcium fluoride. That's our molar solubility. And X comes out to being 3.9 times 10 to the negative 9 molar. And that is our molar solubility in the 0.1 molar sodium fluoride. Let's try another example with a common ion. Calculate the molar solubility of silver 1 carbonate in 0.2 molar sodium carbonate. So first things first, we want to identify what our slightly soluble salt is. And if you don't have your solubility rules in front of you, you'll be able to see one of these is actually written on your KSP chart. So the silver 1 carbonate is the solid that does not dissolve very much, so it actually has a KSP value. Something like sodium carbonate would dissolve in solution because it has a sodium ion in it. So starting with our silver 1 carbonate, we're going to have Ag2CO3 solid that breaks up into 2 moles of silver ions, and we're going to get 1 mole of carbonate ions. Next, we can write the KSP expression. KSP will equal concentration of silver ions, and that'll be squared, times the concentration of carbonate ions. Looking at our sodium carbonate, if we write the dissociation of our sodium carbonate, we'll have Na2CO3 breaking up in solution into sodium ions and carbonate ions, but we're going to get 2 moles of sodium ions when it dissociates. So we started with a 0.2 molar solution of sodium carbonate. So that means that the concentration of sodium ions in solution would actually be 0.4 molar, and our concentration of carbonate ions in solution would be 0.2 molar. We really are not interested in the concentration of the sodium ions because they're just spectator ions. They are not a common ion. The carbonate ion is common to our silver carbonate equilibria. So the carbonate is 0.2 molar, and that's what we really need to know. Next, we can set up an ice table. And we're going to ignore our solid silver carbonate. And initially, we have no ions of silver. And our carbonate we have, and we said that that was going to be 0.2 molar initially from the common ion. When we form some more silver and some more carbonate, they're going to form by plus 2x for the silver and plus x for the carbonate. So the equilibrium line for silver will just be 2x, and for carbonate, it'll be 0.2 plus x. Our KSP value, if we look that up on our chart for silver carbonate, is 8.1 times 10 to the negative 12. And so once again, it's a very small value. They're all going to be very small. So we can ignore this plus x right here. Now let's substitute everything into our equilibrium expression. Our KSP is 8.1 times 10 to the negative 12. Silver is going to be 2x squared. And for carbonate, it's just going to end up being 0.2 since we ignored that plus x. Next, we're going to solve for our x value, which will be equal to our molar solubility. This comes out to being 8.1 times 10 to the negative 12 is equal to 2x squared is 4x squared times 0.2. And then we have 4x squared times 0.2 becomes 0.8x squared. And we can solve for x squared. We get 1.013 times 10 to the negative 11th is equal to x squared if we divide both sides by 0.8. Lastly, taking the square root of both sides to get our x value. So x will equal our molar solubility for the silver 1 carbonate, which is what we're after, and that'll be 3.18 times 10 to the negative 6 moles per liter. Next, let's look at how the pH of the solution can affect the solubility of a slightly soluble solid. We'll use calcium fluoride as an example again. If we write our equilibria for the calcium fluoride breaking up into its ions, we have solid calcium fluoride dissociating into calcium 2 plus ions and 2 moles of fluoride anions. Our equilibrium expression is still KSP equals concentration of calcium times concentration of fluoride ions squared. If we adjust the pH, let's imagine that we add a strong acid to our calcium fluoride solution. The strong acid could be any, but essentially we're really just adding hydronium ion, or if we want to write the shorthand notation, adding hydrogen ion to the solution. We previously learned that the fluoride ion is a weak base. It's weakly basic because it's the conjugate base of a weak acid. That weak acid would be hydrofluoric acid, and so fluoride ion is weakly basic itself. So if you were to add protons to your solution, that weakly basic fluoride anion will be reacted with those hydrogen ions or with those hydronium ions. And so they'll essentially be removed from the solution because they're reacted away, forming a little bit of hydrofluoric acid and a little bit of water from that acid-base reaction. So adding in an acid, adjusting the pH of the solution by lowering it, will remove the fluoride anions. So these are being removed now by lowering the pH. And according to Le Chatelier, we've learned that if you remove something, that equilibria will adjust to shift towards that removal and try to create more. So in this one, it's going to shift to the right towards those fluoride ions being taken away. And so now, in this case, we're shifting away from our solid calcium fluoride and we're shifting towards these aqueous ions. So the aqueous ion side of this is where those are dissolved, or essentially we're increasing the solubility. So by adding in an acid and decreasing the pH of the solution, we were able to react away some of that weakly basic ion, shifting towards the ions, towards the dissolved calcium ions and towards the dissolved fluoride ions, in increasing the solubility of our slightly soluble solid. So our molar solubility of calcium fluoride should increase by dissolving it in a lower pH. Here we have a graphical representation of how the molar solubility of our calcium fluoride will change with pH. On the x-axis, we have the pH, and we're starting out at a pH of 7, or a neutral solution, and it's getting lower or more acidic as we move from left to right. And on the y-axis, we have our molar solubility of the calcium fluoride. So how many moles of calcium fluoride will be dissolved per liter? And we can see that we started out with a molar solubility of 0 at a pH of 7. So really no calcium fluoride is dissolving at a pH of 7 in a neutral solution, or a very, very, very small amount. But then by adding in hydrogen ion and lowering the pH of the solution, we can see that the solubility is increasing exponentially. It's jumping up. When we're at a pH of 1, a very, very acidic solution, the molar solubility is very high. So that means we can get a lot more of that solid dissolved into its ions in solution at a very low pH. And this is true with anions or conjugate bases of weak acids, but we learned that conjugate bases or anions of strong acids, they will not be affected by the pH of the solution because they are really, really, really weak bases, so they have no desire to go back and pick up a proton. So only anions of weak acids like that fluoride anion will be affected by changing the pH of the solution. Before we talk about forming complex ions, which is the third and final thing we're going to learn about that can affect the solubility of slightly soluble salts, we need to learn about Lewis acid-base theory. If you recall, we learned about 3 different types of acid-base theories. We first talked about the Arrhenius theory, which was at the top here. And then we learned about the Bronsted-Lowry acid-base theory. And lastly, at the bottom of the pyramid is Lewis acid-base theory. So Lewis acid-base is at the bottom of that pyramid because it really opens up the doors for a lot of things to be considered as acids or bases that we might not have considered before. Lewis acid-base theory is all about looking at where electrons are going. So a Lewis acid is defined as being an electron pair acceptor. Any substance that can effectively take on an extra pair of electrons can be defined as a Lewis acid. Lewis bases are electron pair donors. They are substances that have an extra pair of electrons that they can give up to a Lewis acid. So in our example below, we have our base with an extra pair of electrons, taking those electrons and donating them to our acid, which is lacking a pair of electrons. It might have a vacant orbital, or it might have a +1 charge as a reason it can take on more electrons. And our product, we form this new covalent bond between our acid and our base. This is often referred to as the Lewis acid-base complex. And we will learn about what this covalent bond is often referred to as, which is a coordinate covalent bond. And it's the same as any other covalent bond that we've previously discussed, but it's called a coordinate covalent bond because both of the electrons came from the Lewis base. So 2 electrons were given to the acid from the base. Let's look at another Lewis acid base example. Here we have NH3 plus H plus forming NH4 plus. We want to define who is the Lewis acid, who is the Lewis base, and show our Lewis base giving electrons to our Lewis acid. So starting off, if we draw our Lewis structure for ammonia, or NH3, we would have a lone pair of electrons on our nitrogen. And our hydrogen ion is just simply H plus because it has already lost its electron. So what's going to happen is our nitrogen is going to donate its electrons to our hydrogen ion. So our ammonia must be our Lewis base. And our hydrogen, which is accepting those electrons, must be our Lewis acid. So when we draw that arrow starting at the nitrogen and going to the hydrogen, what we're really showing is that these two electrons on that nitrogen are now forming a new covalent bond between the nitrogen and the hydrogen ion. So this is why we refer to it as a coordinate covalent bond, because both of these two electrons are being given up from one substance. So then our product, we're going to have our nitrogen, and it would still have the original 3 hydrogens bonded to it, but now we have a new covalent bond formed between there and our hydrogen from our Lewis acid. That covalent bond is the same and equivalent to all other nitrogen-hydrogen bonds, but it has that name coordinate covalent bond. And our product has a charge now because we have a nitrogen that has 4 bonds around it, and so the formal charge on that nitrogen actually is +1. Often brackets are written and the charge is written on the outside of those brackets. The product is referred to as the Lewis acid-base complex. Here is an example of another Lewis acid-base reaction. We have ammonia combining with BF3 to form a nitrogen-borane complex. So if we draw our Lewis structures, we're going to have our nitrogen with its 3 bonds to hydrogen and a lone pair of electrons on the nitrogen. And our Lewis structure for BF3, we're going to have boron with 3 covalent bonds to fluorine atoms. Each of the fluorines would have a complete octet containing 3 lone pairs. And so if we look at who is going to be our Lewis acid, who is going to be our Lewis base, our Lewis base is going to be our ammonia molecule because we have a nitrogen that has a lone pair of electrons on it. Those lone pair of electrons can act as lone pair donors. Our Lewis acid is going to be the boron atom, which can accept those lone pair of electrons. Our boron right now has 6 valence electrons around it. We have 2, 4, 6 from each covalent bond. And so it does not have a complete octet. It would be happy if it had a complete octet containing 8 electrons around it. So how it can obtain that is by accepting a lone pair of electrons from our Lewis base. So we have our Lewis base, which is our ammonia, and we have our Lewis acid, which is our BF3. So our nitrogen will donate its lone pair of electrons to the boron, and that will accept them, forming our Lewis acid-base complex. So now we're going to have a new bond between nitrogen and boron. That would be our coordinate covalent bond. Our nitrogen is still bonded to 3 other hydrogens, and our boron is still bonded to 3 other fluorines, all which have a complete octet themselves. We had 2 neutral species that reacted together, and now we've created some formal charges. Our nitrogen has 4 electrons around it, and it typically likes to have 5 around it, so we have a +1 formal charge on our nitrogen. And our boron is a group 3A element, which typically has 3 electrons around it, and now it has 4, so the boron has a formal charge of -1. So sometimes you start with 2 neutral substances that react to create a complex, a Lewis acid-base complex, where you have formal charges that end up adding to neutral. So we have a +1 formal charge, and we have a -1 formal charge. So the formal charges add up to 0 because we started with 2 neutral species on the left. This bond right here would represent our coordinate covalent bond between the nitrogen and the boron because both electrons came from the nitrogen. We previously learned about small, highly charged metal ions that were Lewis acids that could become acidic from reacting with water in solution. So, for example, the aluminum 3+ ion became hydrated by water molecules and formed a complex ion, such as the aluminum aqua hexahydrate ion. So that's that Al H2O 6 3+ ion. That means that 6 water molecules will surround that aluminum 3+ ion. This is actually a Lewis acid-base reaction taking place. So the Lewis base would be the water molecule, which would have a lone pair of electrons being donated to the aluminum 3+ ion. The aluminum 3+ ion is accepting those electrons, so it would be the Lewis acid. This would actually happen 6 times to form this specific complex ion. So what we end up forming is a charged species. It's going to have a +3 charge because our aluminum had a +3 charge initially. And it's an octahedral arrangement where we have an AX6 type shape, 6 water molecules acting as ligands surrounding our aluminum ion. So in each case, it was from a Lewis acid-base reaction taking place, forming this aluminum aqua hexahydrate complex. And this is just an example of one of the types of complex ions that could form and essentially affect the molar solubility of our slightly soluble salts. I do want to point out that in all of the previous examples where we were showing our Lewis base donating electrons to our Lewis acid, the electrons always started at the Lewis base. So that was where we started our curvy arrow. This is a formal notation used to show the movement of electrons. So the arrow always starts at the tail where the electrons are, and they end or they point towards where the electrons are going. So we have our Lewis base here, and that's where the electrons are starting. So we start drawing our arrow there, and we point them towards the Lewis acid who is accepting those electrons. It's not the other way around. We would not show the arrow starting at our acid pointing towards our base because our acid is an electron pair acceptor. It does not have electrons to donate. It's the base that's doing the donation of the electrons when we form that new coordinate covalent bond.